Hello Precalc BC. Today we're moving on to properties of rational functions, which is pretty much what we're going to spend the next. Okay, so here we go. What is a rational function, you may ask? Well, a rational function is a function in this form r of x equals p of x over q of x, where p and q are polynomials. So this is why we talked about polynomials yesterday, because a rational function is two polynomials being divided by each other. We just have to make sure that q is not the zero polynomial, because obviously we cannot divide by zero, but that generally will not happen. Otherwise, there's like nothing for us to talk about with this type of problem. The domain is the set of all real numbers except those for which the denominator q is zero. Okay, so what we are going to start with is just taking a look at these two examples and finding the domain and the x and y intercepts for each of the following. The first thing we are going to want to do is to do your favorite thing, which is factor. So if I go ahead and factor the top, you should notice you can pull out a 3 from this. But then you can also factor your difference of squares. So that will be 3x plus 5 minus 5. And then on the bottom, I can take out a 4. Okay, so I'll just rewrite this. All right, so what you should also notice is that the x plus 5s are going to cancel. So now I'm going to rewrite my new function, r of x equals 3 times the quantity of x minus 5 all over 4. Okay? Domain. I would recommend we do that next. Even though those x plus 5s canceled, they still factor into our domain. They factor into our domain. Haha, I'm so funny. Okay, as I was saying, if x is negative 5, then we have a 0 in the denominator, which is obviously no good. So our domain will have to be x such that x is not equal to negative 5. All right, now for your x-intercepts, we have discussed in our last chapter at length, an x-intercept is where y is equal to 0. So generally, what makes the most sense is to take your simplified function and to just plug in a 0 for your r of x. And again, my favorite thing to do is to cross multiply. All right, so you'll get 0 times 4 is 0 equals 3x minus 3 times x minus 5, or you can just think of it as multiplying by 4 on each side. Okay, same thing. And then when you go ahead and solve that, you could distribute and solve, or you could just realize, oh, x is going to be equal to 5. Right, because if you divide by 3, or just think of it as factored form, x minus 5 equals 0, and so x is 5. That means our intercept is at 5, 0. For your y-intercept, we have also talked at length that means that x is 0. So generally speaking, I think this is easier to do from the original form, the non-simplified, because you can just start crossing stuff off, right? 0, 0. Whereas if you use the simplified one, you actually have to plug in a 0 and then simplify. That takes too long. So we would just say that r of 0, right, because I'm plugging in a 0, is negative 75 over 20. And then you can just go ahead and simplify that, which I believe is negative 15/4. Right, if you divide by 5. So our y-intercept is 0, negative 15/4. All right, so again, to repeat that, x-intercepts I would find from the factored form, the simplified factored form, and y-intercept I would just plug the 0 into the original non-factored equation. Okay, let's try another one. Definitely gonna have to do some factoring here. So the top, let's see here. It looks like we can definitely pull out a 2 as well as an x, right? A GCF of 2x. So I'll be left with a 2x squared minus an x minus a 1. Yes, good for me. And then x squared minus 8. That's 8 isn't a perfect square, so I'm just going to leave it like this. There is a dumb way to factor it, but we don't need to do that. We can just leave it like this. All right, so now this 2x squared minus x minus 1, that may still factor. Let's see here, 1, 1. Yeah, I think that looks good. Right, it would be 2x squared minus 2x plus x, which is negative 1x. Yeah, so that looks good over here. Equals r of x. Okay, yeah, always once you simplify completely, put your equals r of x or whatever function it is there. Domain. Well, we can't have x squared minus 8 equal to 0, right? So if you do set it equal to 0, you're going to get plus or minus square root of 8. And now here's a very happy pre-calc moment for you. If you want to go ahead and do a factor tree and tell me this is plus or minus 2 root 2, you can go right ahead. But to be quite honest, I really don't care. So if you want to say x can't be plus or minus root 8, go for it. For some people that makes them a little twitchy. They're like, oh God, I gotta simplify that. Then simplify it, it's fine. But what I'm telling you is you don't have to. Okay, x such that x is not equal to plus or minus 2 root 2, that's really easy. So I'm going to simplify it. But again, you can leave it as a root 8. What else do we have to do? X-intercept. All right, so again, my x-intercept, I'm going to go from my final factored form, and I'm going to essentially cross multiply once I have a 0 in for r of x. All right, again, you can also think of it as just multiplying by x squared minus 8 on both sides, which cancels these guys, and then you just have a 0 equals 2x plus 1, x minus 1, and now this is like the one I was talking about before. This is just factored form. You can go ahead and set each of these equal to 0, and you would get x equals 0, 2x plus 1 equals 0, so x is negative 1/2, and x minus 1 equals 0, so x is 1. All right, which means our x-intercepts are 0, 0, negative 1/2, 0, and 1, 0. And I have not left myself really any room for a y-intercept. Hopefully you organize this better than I have. My y-intercept, I recommend going from the original non-factored, because you can just plug a 0 in for x, cancel, 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 cancel. This is a 0 over negative 8, which is a 0. Okay, however, you probably already knew that because 0, 0 was one of our x-intercepts. Okay, so now I want you to notice something about both of these problems. In letter A, the x-intercept turned out to be 5, 0, right? Look at the numerator of your simplified function. See how you had that x minus 5? Okay, and we talked about zeros versus their factored form in our last lesson. Here's your simplified form for letter B, 2x plus 1, x minus 1. And look at what our x-intercepts happen to be. Okay, the numerator of that simplified rational function will always help you reveal your x-intercepts. Okay, so that's a helpful hit to remember. Okay, next. End behavior. This is something we have talked about a little bit before, and then you also talked about it last year. End behavior is basically the behavior of our graph as x approaches infinity or negative infinity, which means all the way to the right and left of our graph. All right, and your end behavior can be either they're going up, they're going down, they're going up and down, or we're going to find also sometimes you are approaching what's called a horizontal asymptote. Okay, so those are your options. What's new to you this year is something called intermediate behavior. Intermediate behavior is the behavior of a graph as x approaches the vertical asymptotes from the left and from the right. Okay, so every vertical asymptote that you have, your graph is going to approach it, and it's either going to be going up or it's going to be going down. It can never cross a vertical asymptote. So what intermediate behavior does is it tells you what is it that your graph is doing. Is it going up or is it going down as it approaches your vertical asymptote? Okay, so we're going to look at this a little more on the next page. R of x equals 1 over x. This is our reciprocal function that we talked about in chapter 2. So we should know that this guy looks something like this, and we're going to do more with something related to the reciprocal function today with graphing transformations. All right, now this does have a vertical asymptote at x equals 0. We'll get into vertical asymptotes more in a minute. And it also has a horizontal asymptote at y equals 0. We'll review horizontal asymptotes more tomorrow. Okay, but for now you can just take my word for it that those are where the asymptotes are. Because our vertical asymptote has an odd multiplicity, the intermediate behavior is different from both directions. Okay, let's look at what that means. Your x down here, that's what's telling you we have a vertical asymptote at x equals 0. It is to the first power. That's why we're saying it has an odd multiplicity, because its degree is an odd number. Whenever your degree is an odd number or you have odd multiplicity, your intermediate behavior is going in different directions. So notice as I'm coming this way, I'm going up. See how I'm approaching the pink line, the vertical asymptote? It's going up. As I'm coming this way from the left, my arrow is going down. Okay, again, intermediate behavior, we only care about what's happening right up next to that vertical asymptote. So if you're asking, well, what's going on with these arrows? Those arrows are talking about your end behavior, because that's as x approaches infinity and negative infinity, not the vertical asymptote. So how would we actually write the intermediate behavior? We would write it like this. As x approaches, the vertical asymptote is at 0, and we're going to say from the right by putting a little plus sign. F of x approaches. Okay, and now here's how you know. Oh, I just erased the graph. You're coming from the right, and your graph is going up. So that means we're approaching infinity. Okay, and then we're going to come from the other side. As x approaches 0 from the left, okay, that's what that little minus is, f of x approaches. Okay, so now you're coming from the left side and you're coming this way. What's your graph doing? Oh, it's going down. So we're approaching negative infinity. All right, now the end behavior is talking about what's happening at the ends of your graph, all the way to the right and all the way to the left. This is what you did last year. As x approaches positive infinity, f of x approaches, and what your arrow is doing is it's kind of leveling out. Okay, what's happening is it's approaching your horizontal asymptote, so it's approaching 0. And as x approaches negative infinity, okay, so that means going to the left, this arrow over here, it's still leveling out, it's still approaching that horizontal asymptote, so f of x is approaching 0. All right, let's try this again, but this time our equation's a little different. This time we have a 1 over x squared. So this is maybe not a function you've seen before. Let's go ahead and graph it. Get rid of all this stuff. 1 over x squared. It looks like this. Okay, so like this. Something like that. This also has a vertical asymptote at x equals 0. We can tell because you have an x squared in the denominator, and if you set that equal to 0, you get a 0. Again, we'll talk more about vertical asymptotes tomorrow. And then this guy's also going to have a horizontal asymptote at y equals 0. Don't worry, we'll get into that more tomorrow. What's unique about this case, though, is because our vertical asymptote has even multiplicity. Okay, look at its degree. It's raised to the second power. So since it's raised to the second power, it's even multiplicity, look what's happening to your two arrows as you approach the vertical asymptote. They're doing the same thing. Okay, over here, your arrows were going opposite directions because we had an odd exponent. Whereas here, they're going the same direction. That's because we have an even exponent. All right, so when we do our intermediate behavior, as x approaches, our vertical asymptote is still 0 from the right. F of x approaches. Okay, so as we're coming from the right, what's your arrow doing? It's going up. So it's approaching positive infinity, or you can just say infinity. And as we approach 0 from the left, it's still going up. So f of x is still approaching positive infinity. All right, now for our end behavior, your arrows are still just approaching this horizontal asymptote of y equals 0. So your end behavior will be the exact same thing. Copy, paste, and there you go. All right, so same answer. Okay, probably could have just told you to write the same thing, but that at least killed some time so that you could write the same thing over again. Okay, let's look at this in regards to graph transformations. Using transformations, graph the rational function, then describe the intermediate and end behavior. Okay, our parent function in this case would be a 1 over x squared. Okay, that exponent, that does become part of our parent function, which we just looked at what that looks like up above. Okay, step 2, think about your transformations. Our horizontal shift comes first. That's this guy right here. So that's 1 over x plus 4 squared, which is left 4. What would come next? Well, a horizontal stretch compress would come next, but that would be right next to x here. We don't have that. So next is vertical stretch compress, reflect, which is our negative 3. Okay, and again, what this is telling you is happening is your y is multiplying by negative 3. Or you can say we are vertically stretching by a factor of 3 and reflecting over the x-axis. Okay. All right, and then finally, we're moving down 5. Okay, all right, so now we're going to graph the parent function. If you plug in a 1 for x, 1 over 1 squared is 1, so we have a point at 1, and then that will also happen when we plug in a negative 1 for x. And then let's just get one more on each side. So if I plug in, so actually if you plug in a 1/2, I know you're probably like, why are you plugging in a 1/2? But if you plug in a 1/2, you get 1 over 1/4, which just becomes 4. So 1/2 comma 4, and it would be negative 1/2 comma 4. And we already know based on the picture above that this looks something like this. Okay, so now let's go through our transformations. 1, 1, I'm going to go left 4. 1, 2, 3, 4. I'm going to multiply my y coordinate by negative 3. 1 times negative 3 is negative 3, and I'm going to go down 5. 1, 2, 3, 4, 5. Okay, now I'm going to do this guy right here. Left 4, 1, 2, 3, 4. Multiply by negative 3. Okay, down 5. All right, right here, left 4, 1, 2, 3, 4. I'm going to multiply by y by -3. Well, I'm already at 4. If I multiply by -3, I'm going to be down at -12, and then I have to move down 5 more. So we can't really fit anything else. Now, question is, how do you draw this? You have 2 points. Well, our horizontal and vertical asymptotes are going to help guide us. So the original parent function has a vertical asymptote at x equals 0. However, we shifted everything left 4. So guess where your vertical asymptote is now? It's at -4. Okay? And your original horizontal asymptote was at y equals 0, but what did we do with everything? We shifted it down 5. So guess where your horizontal asymptote is now? It's at -5. So your graph, your new graph, is going to look something like this. Ta-da! All right, intermediate behavior. Remember, intermediate behavior is as we approach the vertical asymptote, which we have now just said is at x equals -4. Okay? So we'll say as x approaches -4 from the right, and as x approaches -4 from the left. F of x approaches. Okay, and because we had an even degree, you're going to notice your arrows are doing the same thing from both the left and the right. And which direction are they going? They're going down. So what are we approaching? -infinity. Okay. And for for end behavior, we always say as x approaches +infinity and as x approaches -infinity. F of x approaches, f of x approaches. So this end behavior is referring to what's happening to your arrows all the way to the right and all the way to the left. And again, these arrows are kind of evening out at our horizontal asymptote, which is at -5. So we're just saying f of x is approaching -5, and that is on both sides, that it's approaching that horizontal asymptote. All right, our final thing today, we're going to look at this graph and answer some questions. Use the graph shown to find the following information: domain and range, any intercepts, horizontal asymptotes, vertical asymptotes, intermediate and end behaviors. Okay, domain. Well, the only issues we have with our domain here are these guys right here, our vertical asymptotes. And so we're going to say that x, such that x is not equal to, it looks like a plus or minus 1. Okay, range. So range, remember, is referring to what y coordinates we can have. The good news for this one is that if you look, this middle portion, it's hitting everything. So this range is just all real numbers. And I guess since I started in set, I'll stay in set. But you could switch to interval if you want. I'm just going to be consistent. X-intercepts. Okay, well, x-intercepts, looks like there's one right there. So 0, 0. And hey, guess what? That's our y-intercept too. Great. Horizontal asymptote. All right, well, it's drawn in for you. Horizontal asymptote is right here at y equals 0. Okay, and again, we're going to talk a lot more about how to know when you have a horizontal asymptote in our next lesson. For right now, you can either just see it in the picture or like when I told you before, this has a horizontal asymptote, but we will get into that more tomorrow. Vertical asymptote. We have one at 1 and -1. Make sure you actually put x equals because these are lines. And finally, intermediate and end behavior. So notice that you have 2 vertical asymptotes. So that means we have 2 separate statements of intermediate behavior. So I'm just going to get them set up first. So we're going to say as x approaches 1 from the right, f of x approaches, and we'll have to figure out what that is. as x approaches 1 from the left, f of x approaches, we'll figure out what that is. And then, lucky you, you get to do the same thing for x equals -1. So as x approaches -1 from the right, f of x approaches. So this can get a little, it can get a little intense. As x approaches -1 from the left, f of x approaches. I know that looks really obnoxious. Okay, so let's deal with the positive one first. Zoom in. Okay, when you do this, try to completely ignore everything that is not happening around our vertical asymptote. Okay, so literally you're just looking at x equals 1. And as we approach from the right, okay, so actually like go down to where the actual graph is. So to the right is down here because here's the graph. And what is it doing? It's going down. And as we approach from the left, okay, here's the graph. What's it doing? It's going up. So as we approached from the right, we were going down, so that's -infinity. And as we're approaching from the left, we were going up, that's +infinity. Okay, and now we'll do the same thing for -1. Okay, physically cover it up. Okay, so we're approaching -1 from the right. So from the right, I'm coming up here because that's where the actual curve is. It's going up. And from the left, what's it doing? It's going down. All right, so from the right, we have +infinity, and from the left, we have -infinity. And finally, end behavior. End behavior, you don't care about your vertical asymptotes. You're specifically looking at what's happening at the very ends of our graph. And we can see that we're approaching our horizontal asymptote, which is y equals 0. So we'll just say as x approaches +infinity, f of x approaches 0. And as x approaches -infinity, f of x approaches 0. Okay, stay tuned for our next lesson, which is 3.3 part 2. Have a good one.